All right, guys, welcome back to physics. So this week we're going over work and energy. So the first one, how much work is required to stop a 2-kilogram baseball that is moving at 80 meters per second? Okay, a lot of grammar mistakes there, but anyways. So work, so what is work? So we can define work in this situation as the change in kinetic energy. Right, so you did like work on something. So essentially, in this case, if you decrease the kinetic energy, you're doing work on it. But what type of work are you doing? You'd be doing negative work on it. If you increase the kinetic energy, you'd be doing positive work on it, right? And then I could further expand this equation to be kinetic energy final minus kinetic energy initial, right? And then we know the equation for kinetic energy is 1/2 mass times velocity squared, right? So this is final, and then minus 1/2 mass times velocity squared, and that's for the initial. So we know that the initial velocity, our baseball is traveling at 80 meters per second, and then we're trying to stop this ball, right? So our final velocity is going to be 0. So that's really the only variable that's changing is our velocity. So work equals 1/2, and the mass is 2 kilograms. Final velocity is 0. 1/2, 2 kilograms. Initial velocity, 80 meters per second. So then if we calculate, we'll get a work of negative 6,400 joules, right? So that's how much work that it took to stop this ball when it was starting at 80 meters per second. And again, it's negative, right? Because the force, let's say this is a catcher, the force is opposing the motion of the ball, right? So it's going to be negative. If the force was with the motion, like maybe there was wind, right? That was pushing the ball and making it go faster, then the wind would have a positive work on the ball. But in this case, whatever's stopping the ball is going to have a negative work on it because it's stopping the motion of the ball. Come on, I'm having issues here. Okay, so for this next one, a 10-kilogram man travels up an elevator at a constant velocity. If the elevator travels 100 meters, how much work was done by the elevator on the man? So let's draw out what's going on. So we got an elevator, then we got like a man in the elevator. The man weighs 10 kilograms approximately. So what's going on? So the forces acting on this man is the force due to gravity, right? And the force of the elevator, right? Okay. So it's traveling at a constant velocity, right? So we don't have to worry about the forces. So F net is going to equal 0 here, right? And then the elevator travels 100 meters, right? So let's say it's going to travel up 100 meters. So how much work was done by the elevator on the man? So what is the force right here? Essentially, we want to find this force, and then we can plug it into this equation that we know. The work equals force times displacement, right? And we know the displacement here is just going to be 100 meters. So how do we find that force? How do we find the force of the elevator? Well, if we know that the man isn't falling through the floor of the elevator, that means that the force of gravity, right, is going to be equal to the force of the elevator. Because the man's not falling through, the man's not levitating, right? So both of those forces equal each other. So if we find the force due to gravity, then that'll give us the opposing force, right? then we can further dissect this and say that just the weight equals mass times gravity times d, right? You've also seen it look like this, right? An equation that looked like W equals mgh, right? That's potential energy. So, yeah, easy calculation. W equals work equals 10 kilogram man times 9.8, and then displacement of 100 meters, right? And when we calculate it, it's going to give us 9,800 joules, right? And it's positive because the force of the elevator is going in the direction of the motion of this man, right? That makes sense. All right, so number 3. A block of wood is being pulled to the right by a rope at a 30-degree angle to the horizon with a force, so it's a force of 20 newtons. The block moves 100 meters. How much work was done by the block of wood? How much force was done by the block of wood? That should say how much force was done by the rope on the block of wood, and I'll change that. So how much force was done by the rope on the block of wood? Gosh, this is terrible grammar. So let's draw it out. We got our block of wood. And we got our rope. Rope is pushing upwards at 20 newtons, right? 30 degrees to horizon. Okay, so the force right here is 20 newtons. The force equals 20 newtons, and it's at 30-degree angle to the horizon. This force travels 100 meters. This block travels 100 meters, rather. And now it's 100 meters away, right? So how do we find out the work that was done on the block by the rope? So we know the equation, right? Simple equation, work equals force times displacement. But in this case, we have to find the force in the x direction, right? Because this is a diagonal line right here. So we can break it down into x and y components. The y components aren't going to do any work on this block, right? If it's a perpendicular force to the motion, the perpendicular force does not do anything. It doesn't help. It doesn't do any work on the object. So in this case, what we have to do is find cosine of that value, and that'll give us the answer. So work equals 4 times cosine of the angle, right, times displacement. So we plug in our values, 20 cosine 30, displacement is 100. So work then equals, if you calculate it, 1,732. And again, it's positive. Why is it positive? Because it's going in the direction of motion, right? Cool, makes sense. Make sure any force that is perpendicular to motion doesn't count, just cancel it out. And we'll talk about that in the next question. Okay, so this one, we got man carries luggage that weighs 10 kilograms to the front of the line at a constant speed. He travels 10 meters. How much work did the man exert on the luggage? So we got our luggage. Got our luggage. Our man is carrying our luggage and he carries it 10 meters. All right, so now our luggage is over here. So how much work does this man do on this luggage? He's traveling at a constant speed, right? What forces are acting on this luggage? Well, we only really have a force of gravity, and then we have a force of the man pulling, right? Force of the man pulling the luggage up, right? So we don't have any force that is parallel in motion. I'm gonna draw this more to scale. We don't have any force that is parallel in motion to, we don't have a force that is parallel to the motion of this bag, right? So because we don't have any force that is parallel to the motion, then we won't have any work done, right? The man didn't exert any work on this luggage because the only force that this man is exerting on this luggage is perpendicular, right? This one right here is perpendicular to the motion, right? I'm saying this is a motion. So because of that, this man isn't doing any work at all. So, when we do our equation, the force it exerts is 0, and the displacement is 10, right? So that gives us work equals 0. So he doesn't exert any force on this. So make sure that you understand you have to have a force that is parallel to the motion or has some sort of components to it, right? Like in the previous question, where we could break it into its x and y components. The y components do not matter unless they're parallel to motion. But in this case, x components would matter, right? If the luggage was moving up, if the man had been pulling the luggage up, and that was the motion that we were talking about, and we wanted to find how much work he did pulling it up, then we could do that, right? Because he's pulling the forces upward, parallel to the motion, but not in this case. So just watch out for that. Okay, so for this one, 100-gram cube is launched by pulling a spring back 0.20 meters and releasing it. What is the cube's launch speed as it leaves the spring if the spring constant is 20 Newton meters? Ignoring friction. Okay, so let's draw it out. We got our thing. Let's make it orange. We got our spring that's attached to a cube somehow. Okay. And the cube is, in this state, it is pushed backwards. So the spring is in a compressed state. So the original box was over here. Right, let's say this is 0, right, on our coordinate. And then it was pushed back to 0.20 meters. Okay, so if we write down what we got here, the initial position of the box is, it's negative, right? Negative 0.20 meters. The final position equals 0 meters. Initial velocity equals 0, and then we want to find the final velocity, right? So how do we do that? So first thing that we have to do is we have to find out how much work is put onto this block, into this cube by the spring, right? And then after we find out the work, we can use the relationship between work and kinetic energy to find the velocity. So let's find the work first. So we know this equation, right? So the work, let's do a different color. The work of the spring equals -1/2 kx squared. And we're doing it, so this is going to be measured from x initial to x final, right? Initial to x final. So then if we write out the equation, right, work at spring equals a negative, let's do it this way. So I'm going to factor out a negative sign, and then 1/2 k times x squared, and this is the final minus 1/2 kx initial squared. Okay, so I just factored out the negative. And you're subtracting them, right, because it's the change. So, so we know x when we know k, so that we know everything that we need, right? So work spring equals -1/2. K value is 20. X is 0.20. This is final. So this is the x final. So the x final is 0. Squared minus 1/2 times 20 times Now the exponential is just 0.20, and it's negative. It's a negative, but squared, so it doesn't matter. Okay. So now when we calculate this, we'll get a work of 0.4 joules, right? So now we have our work. Now we can exploit our relationship between work and kinetic energy, right? So work equals 1/2 mv squared. So now if we just plug it in, so work equals 1/2 times the mass of the object, which is 100 grams, which is 0.10 kilograms. Let's write it, 0.10 kilograms, and then velocity squared. So we know the velocity, we know the work. I should plug in the work. There we go. So the work is 0.4 joules per hour. So then if we solve for velocity, our velocity is 2.828 meters per second, right? So first thing I did was I found out the work function, right? I found out how much work the spring was pushing on, or how much work it was exerting on this box. And then I used that to find out the velocity using the relationship between work and kinetic energy, right? Cool. So yeah, if you guys have any questions, comment below, sign in. I didn't say that at the beginning, but please do that. And I think we got one more video next week, and then we're good for finals. Yeah, just let me know if you have any questions. Still having my sessions. If you have questions, you can attend those. And good luck on finals. Good luck on everything else we got going on.